Hey everyone, it's West Virginia. All right, so we're ready to tackle this. I am ready for joke of the day. We've got to start with joke of the day because it is the best part of the day. So I'll teach you algebra, trigonometry, even calculus. But graphing, well, that's where I draw the line. Makes me laugh so much. So let's take a look now at polynomials and several variables. So we've looked at how to add and subtract polynomials, but they only had one type of variable in them. Like for instance, it only had an x in it, maybe x to various powers, but only an x. We even looked at being able to multiply polynomials, but again, it only had one type of variable in there, maybe an x. So we're going to look at what happens when we put multiple variables in there. As you can see here, like x's and y's all mixed up together. What happens? Does it make a difference? It makes a difference. But because we know our laws of exponents, everything's going to be perfectly fine. So let's take a look first at adding and subtracting polynomials in several variables. Now what we need to understand is we are going to combine like terms, just like we always have. But we need to remember what like terms are. Like terms have the same variables, and those variables are to the same power. So in other words, as I look at this example and I'm ready to add this trinomial, remember terms are separated by addition and subtraction. So I've got one term here, one term here, one term here, three terms as a trinomial. I'm going to add to that trinomial, this trinomial, one term here, one term here, one term here. But when I add them up, I can only combine up the like terms. So as I look at this, I'm saying, okay, I have an x to the third y to the first power right here. Are there any other x to the third y to the first in there? Sure enough, there's one right here. So I'm going to put those two together, and remember, what's making them alike is the variables, and I like that they're alike. So I'm going to leave those variables alone, and I'm only working coefficients. So I'm going to say this coefficient is a 1, plus this coefficient of 2 is going to give me a 3, and again, that's going to be a 3x to the third y. I am not multiplying any bases. That is the only time I add exponents, when I multiply bases. I'm just combining like terms. That's all I'm doing. So therefore, I'm going to retain what's making them alike. The variables is what's making them alike. So I'm going to leave that alone. So now as I look at this, I go, no, wait a minute. Here's an x squared y squared. Are there any other x squared y squareds in there? And sure enough, there is right here. So I'm going to take this 3x squared y squared, combine it with this negative 9x squared y squared. And again, the variables, I like the way they are. So I'm going to keep them as they are, and I'm only going to work those coefficients. So a 3 minus a 9 will give me a negative 6. So I get a negative 6x squared y squared. As I look on down the line, I see an xy to the third. Are there any other xy to the thirds? Sure enough, one right here. So again, I like that they're alike. I'm not going to mess that up. I'm going to keep that xy to the third as it is, and I'm going to say, well, a 2 minus a 1 is a 1. I don't need to show a 1 as a coefficient, so I can get that out of there. But my point is, here it is, and none of these are like terms because, okay, they all have x's and y's, but this is an x to the third, that's an x to the second, that's an x to the first. This is a y to the first, y to the second, y to the third. They are not alike. So therefore, I am stuck, and that's as good as that one gets. Now remember, whenever you are subtracting polynomials, we learned the shortcut was, this is like saying I've got a negative 1 sitting right here. So therefore, I'm going to multiply that negative 1 all the way through this second parentheses. And recall that when you distribute that negative 1 to every single term in that parentheses, that's why the parentheses is there. To remind me, that negative 1 doesn't just get multiplied to the first term, it gets multiplied to every one of them, otherwise there wouldn't be a parentheses there. But what happens is, it just simply changes all the signs, and once it changes all the signs, then I am back to an addition problem, and I can go back to what I was doing before, where I was combining up those like terms, and because they were alike, I was going to leave those variables the way they were, and I was just going to work the coefficients. So now I've got an x to the third right here with no y's at all, and there's another x to the third right here with no y's at all. So I have one of these, I take out one of these, none of them are left. They are completely gone. They cancel each other out. Moving on down the line, I have an x squared y here, and there's another x squared y right there. So again, I like that they're like terms. I'm going to keep those variables the way they are, and I'm only going to work the coefficients. So a negative 2 plus 3 will be a positive 1. Don't need to show a positive 1 coefficient. Then moving on down the line from there, I have an xy squared And there's no other xy squared, so I can't combine them with anything because like terms have the same variables, those variables to the same power, so that doesn't combine with anything. I'm just going to carry it down. Remember, keep that name tag on there. The sign in front's a sign that goes. Keep that name tag with it. And then finally, this little 4y to the third back there doesn't combine with anything, so I'm going to drag it down, keeping its name tag with it as well. None of these are like terms because, okay, both of these have x's and y's, but that's x squared, that's x to the first, y to the first, y squared, and that doesn't even have an x. So none of these are like terms, and that's as good as that one gets. So hopefully you're seeing that when you add and subtract polynomials, really the rules are no different at all. You just have to be able to recognize where those like terms are and only combine up ones that are alike. So now let's take a look at what happens when you multiply polynomials that have multiple variables in them. And hopefully you're going to see, okay, the rules are pretty much the same. We've just got to be careful about when we actually multiply our terms. So when you multiply polynomials, you need to use that distributive property or FOIL, whichever you want to do, because you can see right here, this would be FOIL, and this would be FOIL. And you can see right here, that would be the distributive property. I just need to be careful about how I multiply those terms. Remember, when I multiply the terms, like for instance here, I'm going to distribute that term through the parentheses, and I multiply 2 times 20, so I'm going to multiply those coefficients. 2 times 20 will give me 40. I just need to be very careful about multiplying those bases. We now know our laws of exponents that say when you multiply same bases, you add those exponents, but only with same bases. So an A times an A, there's same base. It's all about that base, about that base. So I'm going to keep that base, and I'm going to add those exponents. 1 and 2 gives me 3. And then when I do b to the second times b to the third, again, same base. It's all about the base, about the base. So I'm going to keep that base. I'm going to add up those exponents. 2 and 3 will give me 5. Now I've got to distribute that 2ab squared all the way through, even back here. So 2 times 11, again, multiply those coefficients. 2 times 11 is 22. And a to the first times a to the first will be a to the second, because I'm going to add up those exponents on the same bases. B to the second times b to the first will be b to the third. Again, add up the exponents on the same bases. Now, if these are like terms, certainly combine them like you just did, but these are not. Both of them have a's and b's, but this is an a to the third, that's an a to the second. B to the fifth, b to the third. They're not alike. So I'm stuck, and that's as good as that one gets. Now, take a look at this one. Once again, FOIL, extended distributive property, whatever you want to call it. But that means I'm going to take that first term, I'm going to distribute it all the way through the second parentheses. So again, the process is the same, and hopefully that's what you're seeing in all this. The process is the same. I just have to be very careful about multiplying these bases right here. So 5a times 3a, 5 times 3 is going to be 15. A times a, I'm going to add those exponents because I'm multiplying the same bases. So I'm going to keep the base because it's all about the base, add up 1 and 1 and give me a 2. So I get 15a squared. But I'm not done distributing through, so I'm going to take my 5a and multiply. Very careful, name tag right there. Sign in front is the sign that goes. Keep that name tag on the front. 5 times negative 2 is a negative 10. And a times x will be just an ax. So I'm done distributing the first guy through. It's the next guy's turn. So this guy's going to take his turn being distributed through. Being very careful, take out a name tag. That's a negative 6 times 3 is a negative 18. And then x times a is xa or ax. It doesn't matter because multiplication is commutative. And now a negative 6x times negative 2x. Careful about the name tags. Negative 6 times negative 2 is a positive 12. And then x times x is going to be x squared. Same base means add up those exponents whenever you're multiplying. So now I'm looking for like terms, and I do see like terms here and here. And so when I combine up those like terms, I'm going to keep the variables the way they are. That's what's making them alike. I like that. So a negative 10 minus 18 is a negative 28. So I have a negative 28ax. This 12x squared doesn't combine with anything. And this 15a squared doesn't combine with anything. None of them are like terms because this is missing an x, that's missing an a, and these are both first power. So this is as good as that one gets, and that one's done. So now, once again, dealing with FOIL. So I'm going to take my 6x times 2x, and 6 times 2 is 12. X times x is x squared. 6x times negative 4y, being very careful about those signs, 6 times negative 4 is going to be a negative 24. X times y is xy. So I'm done distributing the first term through. I'm picking up the next guy and sending him through. So a 6y times a 2x will be a 12xy or 12yx. It's all the same. And then 6y times negative 4y, well 6 times negative 4 is a negative 24, and y times y is y squared. Now I'm ready to combine up those like terms, and I do see like terms here and here. And I like the fact that they are alike. I'm going to keep those variables because that's what's making them alike. And I'm going to work those coefficients. And so a negative 24 plus 12 is a negative 12. I'm going to drag down my 12x squared that doesn't combine with anything, as well as this name tag. Be very careful. Negative 24 at y squared. None of these are alike, so that's as good as that one gets. All right, so let's take a look at just a couple more examples just to make sure we're very, very good with this when we're multiplying these polynomials. So let me get these out of here and just put just 2 more examples up, again, just to make sure we're very comfortable with all of this. So the next one we're going to look at is going to say I'm taking a 9a plus a 4b and I'm squaring it. Now remember, we talked about this before and we said be very careful. There's my red flag there with the plus sign. So I can't just distribute the power on this one. This one indicates I'm squaring something. That means parentheses times parentheses. It times itself. And when I do parentheses times parentheses, aha, now that means I'm going to FOIL just like I've been doing. So when I FOIL this, 9a times 9a is going to be an 81a squared. And then 9a times 4b is going to be a 36ab. I've sent the first guy through. It's the next guy's turn. Whoops, I forgot my little arrow back there. So it's the next guy's turn, so I'm going to send my 4b through. 4b times 9a is a 36ab. And then 4b times 4b will be a 16b squared. And now I'm ready to combine up those like terms, and I do see like terms here and here. So 36ab plus another 36ab will be a 72ab. Once again, I like that they're alike. I am not going to mess up those variables. I'm just going to work those coefficients. Now this 81a squared doesn't combine with anything. The 16b squared doesn't combine with anything either. And that's as good as that one gets. Okay, one more, just again to make sure we're very comfortable with all this. So let me get this out of here. And the last one that I'm going to go through is going to say x squared plus 1 times an xy to the 4th plus y squared plus 1. So again, the idea here is, okay, parentheses times parentheses, that indicates my extended distributive property. So I'm going to take that first term and I'm going to send it all the way through the second parentheses, multiplying it to every single term. So when I take that x squared and multiply it to xy to the 4th, well, x squared times x, same base right there. I'm going to add those exponents. So I'm going to get an x to the 3rd, but the y to the 4th doesn't really multiply. I mean, it just sits there. Now x squared times y squared is just going to be an x squared y squared. Remember, I can't call it like, oops, I can't call it an xy to the 4th because these are not the same base. I can only add exponents when the bases are the same. This is an x and that's a y, so it's just an x squared y squared. Now x squared times 1 is an x squared. So I've sent the first guy through. It's the next guy's turn. So I'm going to send this 1 through, but interestingly, when I multiply by 1, I just get exactly what I had. So I'm going to get an x y to the 4th plus a y squared plus a 1. Now I'm ready to combine up all my like terms. So I see an x to the 3rd, y to the 4th here. There are no other x to the 3rd, y to the 4th. So I'm going to carry it down. I see an x squared, y squared. There are no other x squared, y squared. So I'm going to carry it down, keeping name tags in the front. I see an x squared. Now there's a y squared, but they're not like terms because they don't have the same variable. So I'm going to carry my x squared down because it doesn't have any like terms. Here's an xy to the 4th, which doesn't combine with anything. I'm going to carry it down. And aha, same thing happens here. And the same thing happens here. So I had no like terms in that. And I do want to point out to you that sometimes that'll happen. You don't always have like terms that you can combine. But hopefully you're seeing now that whenever you add and subtract polynomials that have multiple variables in them, you're doing the same stuff you've already done. You just have to be very careful about recognizing like terms. They have the same variables and those variables are to the same power. When you have like terms, you can combine them up, work the coefficients, keep the variables the way they are because that's what's making them alike. And we like that, so don't mess it up. And then whenever you multiply polynomials that have multiple variables in them, you will continue with your distributive property, FOIL, extended distributive property, whatever you want to call it. But you've got to be careful about how you multiply. That whenever you multiply those terms, you're going to multiply the coefficients and you're going to go back to your laws of exponents. That if they have the same base, you're going to add the exponents, but only when they have the same base. And I hope that helps. Have a great day.